All right, guys, today I'm going to go over the probability ECART. So go ahead and open up your results so that you know which ones you got right and wrong, so that you can compare your answers to the correct answers here, okay? All right, question number one looked like this. Mark had a basket of 40 yellow and 35 white tennis balls. What's the probability that the next tennis ball he randomly chooses will be yellow? Okay, so there are 40 yellow. So that's how many chances he has to pull out a yellow out of the total number of tennis balls, right? Like that's what we're looking at. The total number of tennis balls, which is 75. So 40 out of 75 is the chance that he will randomly choose a yellow ball, right? There's 75 total and there's 40 that are yellow. And then all I have to do with this fraction is simplify. So make sure in Desmos, actually you guys, that key won't be there on the SOL. So practice simplifying or turning this to a decimal. So if I turn 40, because there's multiple answers there, if I turn 40 divided by 75 into a decimal, I get 0.53 repeating. So I know that my answer has to equal that. So 8 divided by 7 does not equal that. That's 1.14. That's not it. 7 divided by 8 equals 0.875. So that's not it. 8 divided by 15 is 0.53 repeating. So all I did was divide those on my calculator to find the decimal, the fraction that equaled the same as this fraction. You're also just dividing both the top and the bottom by 5. So if you are good at simplifying, then you're just doing divided by 5 over 5, which is 8/15. All right, that was question one. Question two. Beth will reach into the bag and randomly choose one balloon. What's the probability she will choose a green? So green, there's 22 greens out of how many total balloons? So 10, 20, 30, 40, 55. And I can divide this by 11 to get 2/5. Correct answer for number 2B. So check your answers and compare them with mine. But that's the fraction that you get when you add up all the total balloons, right? All right, question number 3. In the dartboard below, each small rectangle has the same area. A dart is thrown and it lands in one of the small rectangles. What's the probability it will land in a D? So I'm going to find all of my D's first, which looks like there's only 2. And then that's out of the total number of spaces. So 1, 2, 3, 4, 5, 6, 7, 8, 12, 16. And then I can simplify and I get 1/8. Okay, so 2 out of 16. All right, question number 4. Peter picks one bill at a time and he replaces it every time he does it. Every time he picks one out, he puts it back in to have the same number of bills in there. So he repeats this process 100 times and these are his results. So 28 out of 100 times, he pulled out the $1 bill. And I want to find the probability, the experimental probability, so based on this chart, that is equal to 7 over 25. So 28 over 100, if I divide them both by 4, 28 divided by 4 is 7, and 100 divided by 4 is 25. So it was my first one. But really, you're just putting all of these, like 14 over 100, and then you simplify it. So that what would that be? 7 over 50. So that doesn't equal the 7 over 25. I'm just dividing those by 2. 56 over 100. What's that? 28 over 50. 14 over 25. So that doesn't equal that. So you're just making a fraction out of all of them and simplifying it to see which one equaled that. So it's the $1 bill that was equal to 7 over 25 when I simplified. All right, question number 5. He has a square game board with 25 equal sections, and they're randomly colored, and each player has a chip to toss onto the game board. What's the probability of a player tossing a chip onto yellow? All right, so there are 10 yellow out of 5 plus 5 is 10, 10 plus 10 is 20, 25. And then, okay, so this one wants you to turn it into a percent. So if you do 10 divided by 25 on Desmos, that gives you 0.4. And then to turn a decimal to a percent, you multiply by 100. And that on Desmos gives you 40%. All right. Question number 7 or 6. Question number 6. Jeff put 6 chocolate, 3 vanilla, 4 shortbread, and 7 peanut butter cookies into a bag, and he randomly chose cookies from the bag 20 times, and he chose all of those. So which set of charts below represents experimental and theoretical? Okay, so the theoretical is based on the numbers that he starts with in the bag. So 6 chocolate, 3 vanilla, 4 shortbread, and 7 peanut butter, that's the theoretical. So 6 chocolate, 3 vanilla, 4 shortbread, and 7 peanut butter. So this is the theoretical. The experimental should be chocolate 7, vanilla 1, shortbread 2, and peanut butter 10. All right, so that's not peanut butter. All right, so let's see the chart that has 6, 3, 4, 7 for theoretical. So this one's right. And then, nope, right? The theoretical is based on the actual experiment. So that's wrong theoretical. That's not the correct theoretical. That's the correct theoretical. And now this is the correct experimental. So that's what they wanted you to find in this one. Which of these numbers, like following these numbers, that's theoretical, and then following the times that he picked cookies, experimental. All right. Question number 7. Sean tossed a fair coin 20 times, and here were his results. He thought that the probability of head was the same as the probability of tossing tails, and therefore should have flipped heads and tails the same number of times. So which statement below describes why Sean did not get an equal number of heads as tails? So this is the second day we did probability. We watched that video of the girl who flipped a coin 10 times, and she didn't get 50-50, so she went to a football field, and that did get closer because she had 100 350 people flipping a coin. So this is the law of large numbers. So this is Sean must have tossed the coin wrong. He should have gotten the same. No, he's not going to get the same. He only tossed it 20 times, right? Sean was conducting an experiment. The experimental probability will not always match the theoretical. That's probably it. I'm going to read my other ones just to make sure. The probability of tossing a head is not the same as tossing a tail. Sean's experiment shows you that you are more likely to flip a head than a tail. Nope, you have a 50-50 chance of flipping heads and tails, right? There's not more. You don't have more of a chance of doing one over the other. And D, he needs to flip the coin 4 more times so that his results will be equal. He could flip the coin 4 more times and get heads 4 more times, right? That is not going to make it so that they're equal. So B is definitely the answer. Your experimental doesn't always match the theoretical. However, the more times you do it, it gets closer. And that was the video that we saw. All right, question 8. A student flips a coin 10 times and he got 7 heads and 3 tails. And if the student flips the coin 1,000 times, what would be closest to the expected result? So this one is the law of large numbers, in that if we flip something 1,000 times, the closer you're going to get to 50-50 or half heads and half tails. And if we flip 1,000, then 500 is half. It doesn't matter that this experiment did 7 heads. The law of large numbers is that the more you flip it, the closer it gets to the theoretical. All right, and question 9. A number cube is rolled 12 times, and this chart shows the results. So like they rolled a 1 one time, and they didn't roll a 2 at all. In those 12 times, this is how many times they rolled that number on the dice. If the number cube is rolled 1,000 times, what's most likely to happen? The number 5 will be rolled the most. I mean, just because it was rolled the most now, when you do 1,000 times, that's probably not going to happen. They're all probably going to be close to the same amount of rolls. They will never roll a 2, of course not. If you roll a dice 1,000 times, you're probably going to get a 2 as much as you get all the other numbers. The number of 4s rolled and the number of 6s will be equal. They're not going to be equal. Let me read D. The number of times each number is rolled will be approximately the same. That's a little bit better. C is a little bit too, they're not going to be equal, but they're going to be approximately the same. All of the numbers are. That's the law of large numbers. All right, last question. All right, the spinner has 6 sections of equal size. The arrow of the spinner was spun 60 times, and on 45 of those 60 times, it landed on a section with a multiple of 4. 4, 8, 12, 16, 20. Okay. So what was the experimental probability of the arrow landing on a section labeled with a multiple of 4? This says what's the experimental. That means I have to use the numbers in the problem, like the experiment. And they did this 45 out of 60 times. So I don't even need to look at my spinner. I just need to look at my data. Like this is how many times they spun it and got a multiple of 4, 45 times. And then simplifying this, I could divide them both by 5. So that would be 9 over 12. And I can divide those both by 3 and get 3/4. D. All right. So I hope that helped, guys. If you still have questions on some of these, make sure you ask me before you do the retake. Okay. I want you to make sure you know what you did wrong, and understand probability a little bit better. Okay.